Yes. So can you just confirm me? So my screen is visible to everyone?
Yes, sir.
Okay, okay, okay. Good. Thank you so much. Yeah. So once again, good evening, everyone. So today we have a ninth class and unit number third, that is a control strategies. Okay, and date is a 5th Feb 2024. Okay. So in the previous class, we discussed. Just 1 minute. Yes. Yes. In the previous class, we discussed the overview of type of DC motor, speed control of DC motor, armature voltage control using the transformer, and finally control rectifier feed DC motor. Okay. So so that is from the previous class. There is an overview of the type of DC motor, speed control of DC motor, and armature voltage control of DC motor using the transformer, and control rectifier feed DC drives. Okay. So any confusion, any query from the previous class? Yes, students. So in detail analysis and detailed discussion, we already discussed in the last class. Okay. So now we can take the power electronics converter. Okay, and that is a main topic of the course. So we have to use the power electronics converters, and then we have to control the speed of the DC motors. Okay. So starting with a single phase fully control rectifier control of the DC motors. Okay. And then we will discuss the single phase half control rectifier control of the DC motor. Okay. So today we will discuss these two topics. Okay. So single phase fully control rectifier. Okay, so by using the single phase fully control rectifier, we have to control the speed of the DC motor, and that DC motor may be the your separately excited shunt motor, maybe the series motor, yeah, maybe the compound motor. But in this case, we will consider the single phase separately excited DC motor. Okay, so you can see the figure 1. This figure 1, that is a drive circuit. Okay, so this is an input voltage, that is a Vs. Vs is nothing but Vm sine omega t. Okay, Va is nothing but Vm sine omega t. So that is a supply input voltage. Okay. Okay, so that is a single phase AC. So we can say the 50 hertz supply frequency, correct? And voltage may be the 230 volt because this is single phase voltage. And then topic is a fully control. And whenever we can say the fully control, that means it is a gate circuit, correct? So you can see this is a gate terminal. Okay, so we can say this symbol of the thyristor. Okay, and this is a gate, anode, and cathode. Correct? So we can say we have to control the supply voltage by controlling the gate terminal. And gate terminal is a controllable terminal, correct? So we have a four switch, okay, T1, T2, T3, and T4, that all switches are the thyristor, and we can say this RLE, that is the equivalent circuit of the DC motor. So where RA, that is a armature resistor, LA, that is a armature inductance, and E, that is a EMF, developed EMF. Okay, and that is a IA, that is a armature current. Okay, so we can say we have a simple circuit that is supplied by the fully thyristor. Okay, otherwise you can see the fully rectifier. Okay, so motor is shown by equivalent circuit. Yes, this is equivalent circuit. Field supply is not shown. Yes, for the simplicity we cannot connect the field supply. When field control is required, field is beam from the control rectifier. Okay, otherwise from the uncontrolled rectifier. Okay, so in this diagram we cannot show the field supply, correct? But if you want to connect the field supply, then also you can connect the field supply, and that is a feed by the controllable rectifier, otherwise the uncontrolled rectifier. That is up to you. Okay. So now we have to understand the operation of this circuit. Okay. So how we can turn on this T1, T2, T3, T4, and how we can control the supply voltage, correct? So ultimately we have to control the speed, correct? So we have to control the speed, it means we have to control the voltage, correct? Correct. So we have to control the voltage. Yes. So yes, as I said, so supply voltage, that is a Vm sine omega t, and Vm is nothing but maximum voltage. Okay. Vm is nothing but maximum voltage, correct? Okay. And omega is nothing but 2 pi f, where omega is a 2 pi f, and f is a supply frequency, that is a 50 hertz. Okay, so that is a equation number 1, that is a simple. Okay, so that is a AC input supply voltage. Okay, if the cycle of the source voltage, that is a thyristor T1 and T3, are given the gate signal from alpha to pi, now is a main concept how we can operate the thyristor, correct? So we can say always we can operate the one leg of the thyristor, maybe the upper leg or maybe the lower leg, correct? So we can say this is the upper leg of thyristor, okay, upper leg, and this is a lower leg. Okay, so we can operate one thyristor from the upper leg and one thyristor from the bottom leg, otherwise the lower leg. Okay, and then we can complete the closed cycle. Okay, so if the cycle source, just one time changing the color. Yeah. So if the cycle of the source voltage thyristor T1 and T3 are given the gate signal from alpha to pi. Okay. So duration from alpha to pi. Okay. Suppose your cycle signal is something like that. So this is a sinusoidal signal. Okay. So this is a 0 and this is a pi. So we can say we have to fire the circuit. Student, it is humble request, please join the class on time. Otherwise, disturb the class. Yeah. So now we have to, so you can see this is a sinusoidal signal and we have to operate the thyristor at the alpha because we have to give the firing pulses, correct? So this is your alpha. We can say this is alpha. So we have to operate the alpha to pi. So we can say this is alpha and this time period up to here. So we can operate thyristor T1 and T3. Okay. So T1 and 3T up to alpha to pi. And thyristor T2 and T4 are given to pi plus alpha 2. So we can say again here is a second firing pulses. So we can say from here to, so this is a 2 pi. Okay, so we can say from this alpha to pi period, that is a your T1 and T3, and then pi plus alpha 2, so this is a pi plus alpha. Okay, so pi plus alpha, that is a pi plus alpha to 2 pi, that is a terminable T2 and T4, and this one is a T1 and T3. Okay, so same cycle here is drawn, that is your, here is alpha, alpha to pi. Okay, cycle completed, and second one is a pi plus alpha to 2 pi. Okay, so we have to operate the four switches. Okay, and four switches are the thyristor. So we can operate T1 and T3, that is alpha to pi. Okay, so we can say T1 and T3, that is a alpha to pi, and T2 and T4 form alpha plus pi to 2 pi. Okay, so this is a operation time duration. Okay, so we have to operate our 4 thyristor as per this condition, correct? Because we have to ultimately complete the one cycle, correct? So we can say yes, when the armature current does not flow the continuous, the motor is said to operate in the discontinuous mode. Yes, continuous mode and discontinuous mode. We have a two mode as we discussed in the previous class, correct? So we can say one is a discontinuous mode. So that is the first mode, and second one is a continuous mode. So what is the meaning of continuous and discontinuous mode? So continuous mode, a discontinuous mode means the armature current does not flow continuously. Okay. So it means we can say that motor is operating the discontinuous mode. Okay. And when we can say the continuous mode, when current flow continuously, the conduction is said to be the continuous mode. Okay. So suppose your waveform is something like that, then we can say the continuous mode. Okay, and suppose your waveform is something like that. Okay, then we can say the discontinuous mode. Okay, so you can see from here to here, maybe this time period is a pi and here is alpha plus pi. So this time period is output is a 0, correct? So we can say the discontinuous mode. Okay. So every controller have a two mode, that is a continuous mode and discontinuous mode. Continuous mode means current is flowing the continuous. There is no any disconnection mode, and we can say the discontinuous mode means current is not flowing the continuous. Okay, then we can say the discontinuous mode. So you can see figure 2, that is a discontinuous mode, and figure 1, that is a continuous mode. Okay, so this is a VA voltage, that is a supply voltage, and this is a current, corresponding current. Okay, and this is a negative direction. Okay, because input supply is a positive. Okay, so we can operate the terminal, that is a T1, T2, T3 and T4. Okay, as per the firing pulses. Okay, so ultimately that is a back EMF voltage, we can say the induced EMF voltage, that is a here, because there is a RMS voltage, we can say. Okay. Similarly, there is a continuous mode, that is a figure number 3. Okay. So we can say there is a no zero. There is no 0 degree, correct? So we can say this is a your reference signal. Otherwise, we can say the reference axis. We can operate the thyristor from here to here. Then you can say this is a continuous signal. This is a continuous signal. So that is a VA. Okay. And this is, that is your E. Correct? Okay, so this is your continuous conduction waveform. Okay, so where you can see operate the T1 and T3 and T2 and T4. Okay, done. So this is a simple fundamental concept of the power electronics. I hope you already know this concept, but this is the most important concept to controlling the speed of the DC motor. Okay, yes, any confusion in this slide? Any confusion? Okay, so a drive under the consideration predominantly operate in the discontinuous conduction mode. Okay. So by default, that is operate in the discontinuous conduction mode, because sometimes that is a on, sometimes that is a off. Okay. Discontinuous conduction has several mode of the operation. The approximate but simple method of the analysis is obtained when only the dominant mode of the discontinuous conduction take into the account. Okay, so we have to analysis the both mode, that is a continuous conduction mode as well as the discontinuous conduction mode, and we have to see what is the output voltage in the both case, that is a continuous as well as the discontinuous conduction mode. Okay, The motor terminal voltage and the current waveform for the dominant discontinuous conduction and continuous conduction mode are shown in figure 2 and 3. So you can see in this figure there is a voltage is a VA, EMF voltage, and that is a IA. That is a armature current. Okay. So that is a positive as well as the negative. Okay. And because this is a rectifier, so you will get output voltage that is a DC voltage. So you can see your ultimately induced EMF that is a DC voltage. Correct? That is a constant. Okay. And we have to operate the one by one thyristor switch. Okay. Similarly for the continuous conduction mode. Okay. So how we can operate this switch and what we will get the output voltage, correct? So that is the most important thing. Okay. So in mode of the single phase fully controlled rectifier. Okay. Why fully controlled? Because we have a thyristor and thyristor is a controllable switch. Okay. Current start flowing to the turn on of the thyristor T1 and T3 at omega t equal to alpha. Okay. So we can on the T1 and T3, T1 and T3 at alpha, 8 alpha. Okay. So current is flowing then 8 alpha. So current is flowing. Okay. Maybe any value. Okay. So motor get the connected to the source. Yes, now circuit is in the closed loop. So current is flowing. So motor we can say now motor is start to running. Okay. And it is terminal voltage equal to Vs. That is a terminal voltage, and Vs is nothing but Vm sine omega t. The current which flow against the both, that is a E and the source voltage after the omega t equal to pi. Yes, that is the initial time period. Okay, fall to zero at beta. Okay, so we can say motor is start from here. That is a firing angle alpha from here to here. So here is a pi and then is coming to here. Okay. So you can see this is a zero duration. And then next cycle from beta to again continuous up to 2 pi. Okay. So fall to 0 at beta. Okay. So here is a 0. Here is a 0. So we can say pi to beta duration, that is a your 0 cycle. Okay. So we can say it is a discontinuous conduction mode because that is your only rectifier circuit. Due to the absence of the current, that is a T1 and T2 turn off. So at a time that is a two thyristor is on. Okay, so we can say now T1 and T3 is turned off and we can connect T2 and T4. So motor's terminal voltage is now equal to, it is a induced voltage, that is a E. And what is the value of E? So that is a constant voltage. Okay. When thyristor T2 and T4 are fired, now we have to operate another two thyristor. That is a remaining thyristor switch are T2 and T4 at pi plus alpha. And why alpha? Because we have to give the firing angle, correct? So we can give the firing angle at alpha. Next cycle of the motor terminal voltage, that is a VA. Okay. So you can say we can operate the T1 and T3 at alpha and we can operate the T2 and T4 at pi plus alpha. Okay. So we can say T2 and T4 at pi plus alpha. Okay. So yes, student, this is a most important concept. Huh? So we have to operate the thyristor. So all the thyristor, there is a number of pair one by one using the firing angle. Okay. And firing angle, that is a controllable voltage. So we can say we can control the firing angle and ultimately we can control the firing. Ultimately we can control the output voltage of the rectifier, and that is nothing but the input voltage of DC motor. So ultimately we can control the speed. Okay. Yes. In continuous conduction mode, in the continuous conduction mode, the single phase fully controlled rectifier control of the DC motor, a positive current flow through the motor, and T2 and T4 are conduction just before the alpha. Correct? So because now once the T1 and T3 is turned off, then we can start the second pair of the thyristor, that is a T2 and T4. Okay. Application of the gate pulse is turned on the forward bias thyristor T1 and T3 at alpha. Correct? So that is a forward bias means we can say the positive terminal to positive and negative terminal to negative. Okay. So once the thyristor is forward bias, then it is a conduction mode. Okay. Once the thyristor in the reverse bias, then we can say it is not the conduction mode. Correct? So conduction mode of the T1 and the T3 reverse bias, okay, reverse bias that is a T2 and T4 and turn off them, okay. So whatever transistor are the forward bias, those are the in the conduction mode and remaining thyristor that is a under the discontinuous mode, okay. So cycle of the VA is completed when the T2 and T4 are the turned on. Okay. So once the cycle is completed, so that is a T2 and T4 are the conduction mode, that is a pi plus alpha. Okay. And that time T1 and T3 that is off. Because we have this type of switch, correct? So at a time we can connect the only two leg, correct? So maybe the T1, T2, T3, and T4. So we can connect T1 and T3 at a time, and second time T2 and T4, and then we can say we can complete our cycle. Okay. Yes, since the armature current, that is 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 nothing but your supply volt current is not perfect DC. Yes, it is not perfect DC because the ripple is there. Okay, we know very well in the DC ripple. Okay, so we have to remove that DC ripple by the maybe the LC filter, yeah, maybe the any devices, correct? So normally we use the filter to reduce the ripple. Okay, so since the armature current IS is not the perfect DC, the motor torque fluctuate. Yes, because torque is directly proportional to the current. Correct? Torque is directly proportional to the current and voltage is directly proportional to the speed. Correct? So suppose current is fluctuate, it means your torque is also fluctuate because of the ripple. Since since the torque fluctuate at the frequency of the 100 hertz and this frequency that is a depend on your controller, okay, motor inertia is able to filter out the fluctuation given near the constant speed and ripple less e, okay. So ultimately target is we have to reduce the ripple, we have to reduce the ripple, okay. So how we can reduce the ripple? By controlling firing pulses. Okay. So by controlling the firing pulses, we have to design the control algorithm. Okay. Design control algorithm for what? So that is for the power electronic switches. By using the power electronic switches, we can control the supply voltage. Correct. So that is ultimately our goal. Okay. Yes. Now we can analysis the continuous and discontinuous mode, okay, by mathematical modeling. A subject name that is a modeling and control of the electric drives, correct. So now we have to write the equation, okay. Now we have to write the equation how there is a effect of the voltage and how it is effect of the current on the firing pulses, okay. So same waveform that is repeated here. Okay, so there is a discontinuous mode. Okay, in the single phase fully controlled rectifier, control of the DC motor terminal voltage, there is a VA. VA is nothing but your armature voltage. Okay, so VA is nothing but your armature voltage. Operates in the two interval. Okay, so first interval that is a duty interval and second interval that is a zero current interval. Okay, so what is the meaning of the duty interval? Duty interval that is a duration between the alpha to beta, and alpha to beta that is a nothing but zero crossing. So you can see here is a alpha, so here is a alpha and here is a beta. Okay, so this duration that is your duty interval. When rotor motor is connected to source, that is the VA equal to Vs, and Vs that is a supply voltage, and Va that is a armature voltage. So you can see from the waveform, so this duration, that is your connection time period. Okay. And second duration, that is a zero current interval. And what is a zero current interval? So that is a this time period, beta to pi plus alpha, because that is a negative cycle, because we have an input that is a positive cycle. So positive, then negative, correct? So we can say beta to pi plus alpha when Ia is equal to 0 and Va is equal to E. So we can say the zero current interval. So what is the interval for zero current? That is a beta to alpha plus pi. And what is the duty interval? That is alpha to beta. That is your duty interval. Okay. So now we can write the equation. Yes, for the voltage. Okay. So based on these two equations, based on these two conditions, there is a duty interval as well as the zero current interval. We can write the equation. So we can say VA equal to RAIA plus L di by dt plus E. Okay. So this is a simple equation. We can say this is a supply voltage. Sorry, we have a circuit. So this is your supply voltage. Okay. Here is your motor. RA, LA, and E. So we can say E, LA, RA. So this is a VS, and we can say it is a armature current. And VS is nothing but VS equal to Vm sine omega t. So now just apply the KVL in this loop. So KVL is nothing but Kirchhoff voltage law, correct? So just apply the KVL in this loop. So we will get KVL is nothing but V equal to IR, correct? So voltage source is equal to I into R. So we can say VA is equal to RA IA, correct? So RA into IA plus LA di by dt. So inductor voltage across the inductor, what is a inductor voltage? So we can say VL equal to L dia by dt, correct? So voltage across the inductor, that is a L dia by dt, plus this is a again voltage source. So we can say the induced EMF, that is a E is equal to Vs, that is a Vm sine omega t, and that duration is alpha to beta. Okay, so that is equation number 2. Okay, so that is simple equation. Just we have to apply the KVL for the single phase DC motor. Okay, that is a fed by the single phase fully controlled rectifier. Okay, so this is a Vs, current is flowing the IA, and we have a simple equivalent circuit of the DC motor. So we can say the RALAE. Okay, and VL is nothing but LDI by dt. That is equation number 2. Now VA is equal to E and IA is equal to 0. Why IA is equal to 0? Because of the discontinuous mode and that time duration, that is a beta to pi plus alpha, and that is a second duty cycle, second duration, correct? So we can set the zero current interval. Okay. So first interval, that is a duty interval, and second interval, that is a zero current interval, correct? So in the zero current interval, we already discussed that is IA is equal to 0 and back EMF is equal to VA. Correct? So same condition here I written. So VA is equal to E and IA is equal to 0 at what condition? That beta less than equal to omega t and less than equal to pi plus alpha. That is equation number 3. Okay. The solution of equation 2 has the two component. Okay. So solution of the equation number 2, that is a big equation. Equation number 2 has the two component. Okay. One due to the AC source, that is a Vm by Z sine omega t minus phi. Okay. Because of the AC source, Vs equal to Vm sine omega t. So we can say there is a impedance. Z is a impedance. Okay. So Vm by Z sine omega t minus 5. And second component, that is due to the back EMF, that is a minus E upon RA. Okay. So we have a two components for the equation number 2. Okay. First one, that is due to the AC voltage source Vm by Z sine omega t minus 5, and second one, that is a back EMF, that is a minus E upon Ra. Okay, we have these two components for the equation number 2. Each of these component has the turn in the transient component. Yes, let this be represented by the exponent. Okay, there is a k1 e की power minus t upon rho a. Okay, so that is a transient response. We can say that k1 e की power minus t upon rho a, and rho a is nothing but your time constant. Rho a is nothing but your time constant, and that value is a L by R. Okay, so tau A is nothing but your time constant, and that value is a L by A. And we have what is a L? L, that is a LA, and what is a R? R, that is a RA. Correct? Okay. So this condition we have to now derive. Okay. Yes. So we can say again, we can rewrite the equation. There is a IA equal to Vm by Z sine omega t, because in previous equation you can see this is a VA, okay, RA, VA equal to RA into IA plus L di by dt plus E, okay. So we can rewrite the equation as per the two component, that is a Vm by Z sine omega t minus 5, and second component, that is a minus E by RA, okay. So we can rewrite that is a IA equal to Vm by Z sine omega t minus 5 minus E by RA plus K E minus T की power rho A for alpha to beta. Okay, so during the on time period. Okay, where what is a Z? Z is nothing but impedance, and whenever we can say impedance, that is a RA square plus omega LA square. Okay, so this simple impedance. Okay, you know very well about the power system, and all of you working in the mostly all of student working in the power system, correct? So that is in the power plant. So impedance is nothing but the under root R square plus omega LA square, correct? And what about the phi? Phi is nothing but the angle, that is a tan inverse omega L by RA, correct? That is equation number 5 and 6. So Z is a impedance and phi, that is an angle. Constant K1 can be evaluated subject to the equation number 4 to be the initial condition at IA equal to 0. Okay. So we can find out the constant K that depend on the circuit parameter. But for the simplicity and the simple calculation, we can say IA alpha is equal to 0. Then we can easily calculate the constant Ka. Okay. So substitute the value of the K1. So obtain the equation number 4. Okay. So what is the value of the K1 now? So yes, we have to substitute the IA equal to 0, okay, in the equation number 4, okay. So we can say IA omega t equal to Vm by Z sine omega t minus 5 minus sine alpha minus 5 e की power minus omega t minus alpha cot 5, okay, minus e की power upon alpha e upon r a 1 minus e minus omega t minus alpha into cot theta for alpha to beta. Okay, so this equation, how we can get this equation? Equation number 7. This is a simple. What we have to do? Yes, constant Ka can be evaluated subject to subjecting the equation number 4. Yes, so this is equation number 4 to the initial condition, that is Ia alpha equal to 0. Okay, so we have to consider the initial condition, that is Ia is equal to 0. Substitute the value of the K1, so obtain the equation number 4. Okay, right? So this is equation number 7, correct? And cot is nothing but cos upon, that is a ratio of the cosine and the, yes, ratio of the cos and sine, that is a cot, correct? Otherwise, we can say 1 upon 10, that is your cot, correct? Since the Ia beta is equal to 0 from equation number 7, yes. So we can consider the I beta is equal to 0. So we can say Vm by Z sine beta minus 5 minus E upon Ra, correct? So this equation number 8. So that is a Vm by Z. Yes, Vm by Z sine omega t minus 5. So because we have to consider the Ia beta is equal to 0. Okay. So beta minus 5 minus E upon Ra. So there is a minus E upon Ra plus E plus Ra minus Vm by Z sine alpha minus 5 into, so we have to consider this term now. Okay. This term here. So we can say this term is here. Sine alpha minus 5 into E minus beta minus alpha cot 5 is equal to 0. That is equation number 8. Okay. So beta can be evaluated by the iterative solution of the equation number 8. Okay. So suppose you want to find out the beta, so we have to do the iterative solution. Okay. And then we can find out the beta value. Okay. So yes, what is the iterative solution and how we can find out the beta? So we have to consider the integration limit, that is a turn on time period and turn off time period. Okay. Since the voltage drop across the armature inductance due to the DC component, yes, we can say we have this inductor, okay, and we have a DC supply, correct? So here is a armature drop, correct? VL. We can see the armature drop, okay, VL, okay, correct? So yes, since the voltage drop across the armature inductance due to the DC component of the armature current is 0, so we can say VA equal to, yes, VA equal to E plus IARA. This is a fundamental voltage equation. Fundamental voltage of motor. Correct? Where VA and IA are respectively DC component of the armature voltage and the armature current. Correct? So that is a IA and VA, that is armature voltage and current. Okay. So now we have to apply, that is alpha to beta, first condition, and second one is a beta to pi plus alpha. There is a second condition. Okay, because we have to operate the switch, correct? So we can say now we can do the integration for the alpha to beta and beta to, yes, alpha to beta and beta to pi plus alpha. So you can see for the half cycle we have a one cycle, correct? We have this cycle. So here too we can operate this one, and here to here. So we can say this is alpha, this is a pi, and this is a beta, correct? And then again, it is a, we can say again, this is a continuation with this here, correct? Done. So we can say alpha to pi, alpha to beta. So this duration, and pi plus beta, this duration. Okay. So we have to do the integration, correct? So we have to find out the voltage, correct? So how we can find out the voltage for the positive cycle integration and negative cycle integration, correct? So alpha to beta, okay. So Vm sine omega t. So there is nothing but the Vs, and this is nothing but the E, okay. Beta to pi plus alpha, okay. So this is simple integration for, that is a one cycle. So you can see the 1 by pi, okay, correct. So there is a half cycle, not the full cycle, half cycle. We are doing the integration for the half cycle, correct. So we can see integration of the Vm sine omega t. So what is the integration of the sine omega t? That is a cos omega t, correct. So Vm cos alpha minus cos beta. Why alpha minus beta? Because of the here is a lower limit is alpha, upper limit is a beta. Okay. An indication of the sign there is a cos. So cos alpha minus cos beta plus integration of the e. So e is a constant. Okay. So we can say the pi plus alpha minus beta into e divided by pi. So that is a integration of the VA. Okay, so ultimately VA is this equation. Okay, so armature current consists of the DC component, that is a IA and harmonics. Yes, obvious that is a DC component because here is a rectifier. Correct. When flux is a constant, only the DC component produce the steady torque. Okay. Harmonics produce the alternative torque component, the average value which is the zero. Yes, because of the ripple and because of the DC harmonics and produce the alternative. So we can say positive negative is cancel out. So we can say harmonics produce the alternative torque component, that is your zero. Okay. Therefore, yes, therefore, the motor torque is still given by equation number 7. And what is equation number 7? Yes, this is equation number 7. That is a motor current, correct? Yes. So motor current, so that is a torque is directly proportional to the current. We can say torque is directly proportional to the current, correct? So from equation number 7, 8, 9, and equation number 8, so we can say omega m, that is a Vm. So this is nothing but your Va equal to Ia Ra plus L di by dt plus E. This fundamental equation. And second one, that is a omega directly proportional to the V. And third one, that is a Ia directly proportional to the torque. So using this equation, we can derive this equation. There is a Vm cos alpha minus cos beta divided by k beta minus alpha minus pi into Ra k square beta minus alpha into t. So this we already discussed this equation in the last class. Okay, so Va equal to Ia Ra plus L di by dt divided by di by dt plus E. Correct. And speed is directly proportional to the voltage and current is directly proportional to the current. So we can derive by equation number 7 and 8. By equation number 7, 8 and 9 we can calculate. Yes, we can find out this equation, that is a omega in the form of the supply volt in the form of the maximum voltage, in the form of the beta and alpha, in the form of the torque, correct? So now you can see, suppose you want to control the speed, so we have to control the alpha beta, correct? And how we can control the alpha and beta? By controlling the firing angle. And how we can controlling the firing angle? By using the PI controller. Okay, so ultimately we have to design the PI controller to control the firing angle of the alpha and beta. Yes. So boundary between the continuous and discontinuous conduction mode is reached when beta equal to alpha plus pi. Okay, so there is a boundary condition, that is a beta equal to pi plus alpha. Okay, so substitute beta equal to pi plus alpha in equation number 8. Okay, so now we have to substitute the equation value of the beta, and that is a boundary condition. Okay, in equation number 8. And what is equation number 8? So that is equation number 8 is this one. Okay, so here we have to put the value of the beta. Yes. So gives the critical value of the speed, that is a omega mc. So omega mc is nothing but critical speed of motor. Okay. So omega mc, which separate the continuous conduction from the discontinuous conduction for the given alpha. Okay, so this is a, we can say this is a boundary range, that is a boundary condition, not the range, boundary condition, that is a beta equal to pi plus alpha. Okay, so finally we can say critical speed is equal to Ra into Vm divided by Zk sine alpha minus 5 1 plus e power minus pi cot 5 divided by e की power pi cot 5 minus 1. So there is a critical speed of the DC motor, and that is equation number 12. Okay. Yes. So till equation 12, from the equation number 1 to equation number 12, that is a fully controlled rectifier fit the DC motor with the discontinuous mode. Okay. So discontinuous mode is little bit tough because that is a, we have to consider the alpha and beta. Okay. But compared to the discontinuous mode, continuous mode is a very simple. Okay, compared to the discontinuous mode, continuous mode is a simple. Okay, so now we can discuss the continuous conduction mode. Okay, continuous conduction mode means that current is continuously flow in the circuit. Okay, so there is no zero crossing point. Okay, from figure 3, so yes, this is a continuous conduction mode. Okay, so from figure 3, we can say this is a continuous conduction mode. Okay, so for the half cycle, we can say VA equal to 1 by pi. So for the half cycle from here to here, okay, so during this time period, we have to find out the voltage. Okay, so the for half cycle we can say integration alpha to pi plus alpha Vm sin omega t, again this is a Vs, so we can say integration of the Vs, sorry, integration of the sine, that is a cos, so we can say ultimately 2Vm by pi cos alpha. Okay, so this is simple integration of sine, there is a cos, and there is alpha plus alpha, there is a 2Vm. Okay, divided by pi cos alpha. Okay, so this is a simple output voltage of the VA for the continuous conduction mode. So we can say VA equal to 2Vm divided by pi cos alpha. So that is a finally output voltage for the continuous conduction mode. Okay, so from the equation number 7, 8, and 9, again that is the same equation. Okay, so VA equal to RA IA plus LDI by dt, VA equal to Ra plus La dia by dt plus E. Okay, and that speed omega is directly proportional to the speed, sorry, voltage, and torque is directly proportional to the current. By using this equation, we can derive this one. Okay, so that is equation number 14. Okay, so that is omega m is equal to 2Vm divided by pi k cos alpha minus Ra divided by k square into t. Okay, so this is a speed for the continuous conduction mode. Okay, so by continuous conduction mode, we can control the speed of your motor. Okay, yes. So now we can define the like boundary condition between the continuous mode and discontinuous mode. Okay, so you can see the figure 4 speed torque characteristic of the single phase fully controlled rectifier fit DC separately excited motor. Okay, so this is a, we already discussed this characteristic, that is your simple VI characteristic of the separately excited motor. Otherwise we can say the speed versus torque characteristic. Okay, here is a more curve because of the different angle, different firing angle. Okay, so you can see the at alpha equal to 0 degree, at alpha equal to 60 degree, at alpha equal to 90 degree, alpha equal to 120, and alpha equal to 160. Okay, so you can see, suppose you operate your rectifier at alpha equal to 0 degree, so you will get this response. So that is a corresponding to Vm by k. Suppose you will operate the alpha equal to 60 degrees, so you will get this characteristic. Okay. So we can say this is a boundary condition. So this is your boundary condition. So continuous conduction mode and discontinuous mode. So this region, that is your discontinuous conduction mode. So this region is a discontinuous conduction mode, and this region, that is your continuous conduction mode. So this region is a continuous conduction mode. Okay. So this is the limitation, otherwise we can say the boundary condition for the continuous and discontinuous conduction mode. Okay. So yes, we can say therefore alpha less than equal to less than pi by 2, E should be greater than or equal to the Vm. And when alpha greater than pi by 2, E should be the greater than or equal to Vm sin omega t. Therefore, no load speed is given by, okay, so no load speed, what is a no load speed? Okay, so no load speed is nothing but Vm naught, Vm dot is equal to Vm by k, okay, for 0 to pi by 2, there is a half cycle. Otherwise, we can say Vm is nothing but Vm sine alpha divided by k. Okay, for the pi by 2 less than pi by 2 to pi. Okay, so there is equation number 15 and 16. Okay, so we can say there is a no load speed. Okay, the maximum average terminal voltage, that is 2 Vm by pi, is chosen equal to the rated motor voltage. Okay, so ideally no load speed of the motor when fed by the perfect direct voltage. Okay, that is a 2 Vm by pi k. We already derived that 2 Vm by pi k, correct? 2 Vm by pi k, correct? Yes. It is interesting it note that the maximum no load speed with the rectifier control is pi by 2, and pi by 2 is nothing but half cycle. Okay. The boundary between the continuous and discontinuous conduction is shown by the dotted line. Yes, we already discussed the continuous and discontinuous conduction mode. There is a speed versus the torque characteristic. Okay, so where we have to operate the continuous conduction mode and discontinuous conduction mode. For the torque less than the rated, the low power drive mainly operate the discontinuous conduction mode. For the less torque, okay, the torque less than the rated, a low power drive mainly operate in the discontinuous conduction mode. Okay. In continuous conduction mode, the speed torque characteristics are parallel straight lines. Okay. So according to the equation number 14, so this is not 5.84, but it is a equation number 14. Okay, depend on the armature circuit resistor, there is a Ra. Okay, the effect of the discontinuous conduction is make the speed regulation is poor. Yes, because it's a zero condition, so we can say speed regulation is poor in the discontinuous conduction mode. Okay, and that we already explained in the figure number 2 and 3, where is a continuous conduction mode and discontinuous conduction mode. Yes. Okay. Now, what about the regenerative braking? Okay. So, what we can do for the maybe we can say the second quadrature operation and fourth quadrant operation, that is a regenerative braking. Okay. In the continuous conduction for the given the alpha, any increase the torque, that is a omega m. Okay. Suppose you increase the torque. Okay, and E to drop due to the that IA and T can be the increase. Yes, that is a, we can say the relation omega, we can say the relation speed, omega, torque, current, and voltage. Suppose you increase or decrease any one quantity, that is a depend that effect on the another quantity, correct? Average terminal voltage VA remains the constant. Yes, VA is remains the constant, that is armature voltage. In discontinuous conduction, any increase in the torque and a complete increase the IA. Yes, torque is directly proportional to the current. Cos is B to increase and VA to drop. Yes. Consequently, speed drop by the large amount. Yes, that is a speed drop, that is a large amount. The drive operate in the quadrature first, that is a forward motoring. We already studied this is a forward motoring, reverse motoring, forward braking, reverse motoring, and reverse braking. Who want to join the class now? Now class is the, yes, Danjit. Danjit, you are too late. Yes, so we can say, yes, Vanita. Yes. So on the y-axis we can say the speed, and on the x-axis we can say the torque. Okay. The drive operate in quadrant one, there is a forward motoring, and fourth there is a reverse generating mode. So first one is a forward motoring, and fourth one there is a reverse motoring. Correct. So you can see the 2 Vm by pi. So there is a Va versus the alpha. So here is a, so this is a first quadrant and this is a fourth quadrant. So here you can see the minus 2 Vm by pi. So we can say the reverse braking. Okay. And this is a forward motoring. Okay. So similarly, we can say the motoring mode. So you can see here is a, we can say the rectifier, positive and negative, positive and negative. So we can say the fully controlled rectifier feed your DC motor drive. Okay. So yes, that is a angle is a 90-degree, obvious. Yes, regenerative mode, correct. So again, it's a regenerative mode. So there is a, like alpha is a 90-degree. Okay. So that is a regenerative mode operation. Okay. So regenerative mode also we can say the inversion. Okay, because that is a generate the energy. Okay. So in the normally we can give the energy to the motor, but in the case of the regenerative, so we can produce the energy from the sorry, we can produce the energy from the motor. Okay, so it is a work is a generator mode. Okay, yes. So till now we discussed the single phase fully controlled rectifier, that is a conduction mode as well as the discontinuous conduction mode. Okay, so from the next class we can discuss with the single phase half control rectifier. Okay, there is a similar to the similar to the single phase fully controlled rectifier, but in the case of the half wave, in the case of the half wave rectifier, now we have a two switch and two diode. So you can see we have a two thyristor. So we can say the T1 and T2 thyristor, D1 and D2, that is a diode. Okay. So instead of the four thyristor, we have a two thyristor and two diodes. And similarly, we can connect the R, L, and E. Okay, that is a simple your motor. Okay, so we can say again supply voltage, there is a Vm sin omega t. Okay, similar to the previous case. Okay, and then we have to operate the one by one. There is a one leg, sorry, we have to operate the two leg, but there is a one switch from the upper leg and another switch from the bottom leg. Okay, so we can say we have to operate the T1 and D1 at a time, and D2 and T1 at a time. Okay, so at a time operation, at a time operation, there is a T1 and D1, and second time T2 and, so T1 and D1. So this is a T2, T2 and D2. Okay. So we have to operate your switch. Okay. So you can see T1, D1 and T2 and D2. So this is a discontinuous mode. Okay. And this is your firing pulses alpha. Okay. And similarly, this is your continuous mode. Okay. So, mathematical equation we will discuss in the next class. That is a discontinuous conduction mode and the continuous conduction mode, because this is a too complex thing. So maybe you cannot remember all this thing. Okay. So we will continue from the next class. That is a discontinuous conduction mode and continuous conduction mode uh, for the uh, single phase half control uh, rectifier feed the DC motor. Okay, so we can continue with the next class, that is a single phase half control rectifier feed DC motor drives. Yes, student. Any query, any confusion from the today's class? Today's class, that is a most important class, because of that is we have to control the DC motor by power electronics circuit. Okay, and you have to implement this a single phase fully control rectifier as well as the single phase half control rectifier in the MATLAB. Okay, so thank you so much. If you have any query, then please let me know. Okay, then thank you so much, but you have to implement this single phase half control and single phase fully control rectifier in the MATLAB. Okay, yeah, thank you. Then now you can leave.